Hello everyone, for this tutorial video I like to talk about simple machines, as well as the math/logic behind how to predict how they will work. A simple machine is any device that allows you to reduce the input force needed to do the job you want. A ramp being a good example of this. We can predict, because we know, work equals force times displacement in the exact direction of the force. If the distance is longer, the force must be less for the work to be the same. And if the distance is shorter, the work must be greater. And this actually explains why a ramp works. Because the longer distance on the narrower angles allow you to use less force for the same amount of work done. And similarly, if the slope is steep so it has a small hypotenuse or distance, then the force required to do the work is greater. This should make intuitive sense because the steeper the slope, the more gravity will work against you, and the shallower the slope, the closer it is to level ground. Although I explained it in terms of work done, because many simple machines will not be this obvious. So we can use work done to explain the more complicated machines as well. In particular, if we examine a pulley, we see if it is one rope with one wheel, then the force at the input is still exactly equal to the weight at the output. But if we use a two-wheel system, so that the overall distance of the rope is greater, then the force must be lesser in order for the same amount of work to get done. So this means ignoring factors such as friction. A two-wheel pulley will give you exactly twice the force you input, without you actually having to exert twice the force yourself. A wedge, like you might see on a nail, can be thought of as two inclined planes back to back. So the same general thought process holds for them as well, namely that if the edge is narrow and blunt, it will not give you as much output force for the same input compared to a sharper tip, because a sharper tip has the longer ends of the inclined plane, so we'd expect to have to do less force for the same amount of work. The other three most common types of simple machines, the lever, wheel and axle, and screw, all involve rotational motion rather than the simple linear motion, so we will have to remember the appropriate equations from rotational motion. If we chose to study something such as a nail puller or crowbar, we would first diagram out every single major force on the system. So there's the force you exert with your hand on the edge of the crowbar, the output force on the other end of the crowbar, the force of the nail, and the normal force supporting the place where the crowbar meets the table. And the place where the crowbar meets the table is where it will rotate around. And you will hear it technically called the pivot, or even more technically the fulcrum, where the word pivot might make sense from everyday contexts, as in the phrase pivotal movement, or you may have heard it used in dancing or sports contexts, like pivot on your toes or pivot around your arm. But the other word fulcrum may seem like it comes out of nowhere, but like the word torque has a logical etymology from Latin, where it comes from Latin where it literally means post of a couch. So the fulcrum is the post, or the stationary point that you are rotating around. We know already that forces rotating around a pivot are called torques. So this means the torque at the input equals the torque at the output, which must be true logically if the nail and crowbar are not moving. Because if a torque is greater on either side, then the crowbar will rotate, which is not the case. So now we can rearrange the equation to state that the output force over the input force equals the input length over the output length. And this actually has a specific name of mechanical advantage, as a reference to the fact you get a better force. than if you just tried moving it by hand. We can practice problem solving on different machines that are not directly related to a crowbar, so that we develop a true understanding of how these problems work and are not simply memorizing formulas. If we looked at a wheelbarrow and we want to analyze only the lever part of it, ignoring the wheel, so the part with the handles, then we see it pivots around the center of the wheel, as that is where the lever is screwed on. The input force would be at the end of the lever, and the output force would be the load or weight inside the wheelbarrow. And since it is a lot heavier than the wheelbarrow, it would bias the wheelbarrow's center of gravity toward that. So now that we know exactly where our inputs and outputs should be, we can measure the distances and state that the torques are equal as well, in order for the lever to be balanced and not to rotate toward the ground. So we see here, although it does it in a different way than the crowbar, the lever also gives us a mechanical advantage, which again is the ratio of the output force to the input force. But this is true for any type of lever, regardless of how exactly it looks. So lastly, if we are given a shovel carrying a heavy load, and we hold it as shown in the diagram, we see in this case the pivot is the end of the shovel. The input force is wherever you choose to hold it along the handle of the shovel, and the output force is the weight you wish to move, exactly like with the wheelbarrow. We see unfortunately here the mechanical advantage is less than 1, so it is actually harder to move it than if you just moved it by hand, because of the fact the output force has a greater length than the input force measured relative to the pivot, whereas in the previous two examples the inverse was true, i.e. the output force had a shorter length. So now that we know how levers work, we can use this to deduce how cranks and wheels work. In particular, if we were to study the crank carefully to determine what its mechanical advantage would be. We see when you rotate the input, you exert a torque, just like when you rotate anything. And at the output, there is also a torque because there is a force rotating an axle on the crank. So it should become obvious that the mechanical advantage of a crank is simply the input force to the output force, exactly like how it works with levers, even though it works entirely different. So now we can deduce that this works for wheels as well, because wheels rotate in the same exact way that cranks do. So we conclude that its mechanical advantage must also be the ratio of the radiuses. Now that we have exhaustively explained how simple machines work, we are ready to discontinue talking about mechanics and talk about a special type of motion that is not covered under general mechanics, called vibrational motion or oscillating motion, where the motion is an up and down pattern, so something like a spring or pendulum. Don't forget to subscribe if you found this video informative, and make sure to see other tutorial videos, and follow me on either Facebook or Twitter for more content.